get started. So there's a lab due this week, and I've been getting lots of last minute requests saying can we have an extra day or two or some such thing. So I just posted on the forum this morning saying ideally you should have all started, but having said that, I'm happy to accept it on Friday instead of Wednesday if you want. Okay. That will not give us any extra time for lab 3. Lab 3 is still going to come out later this week and it will be due in the last week of classes. And since the semester ends, there isn't any room to give more time at that point. So make sure to plan for lab 3 well. Okay? But lab 2 you can turn it in on Friday and I will not accept, I will not assess late penalty or anything like that as a one-time extension. Okay. There was a homework that was supposed to go out for a variety of reasons. I think I couldn't put it up, but then since it was going to be due right around the time the lab was due, I held back a little bit. I will put it up and I'll have it due next week. Okay, so if you turn in the lab later this week and have the homework coming next week, you should still be good. Okay.
Are you doing more quizzes?
Sorry?
Are you doing more quizzes for the
There should have been. I think the TA was supposed to put up a few ways on Friday. He did not.
I haven't seen it since
Yes.
the midterm.
There was a good one.
There was?
Yeah.
Okay.
Why did you skip quiz it?
Okay, so I think there was one quiz we skipped around the spring right after spring break, but we should have resumed it. So just check if there's an issue, let me know. Okay, I was assuming there was quiz. Yeah, and it's okay if you miss a quiz or so because the quiz has very few points as compared to the quiz. Alright, so let's get started. We were talking about fault tolerance and distributed commit as a way to have all or nothing even in the presence of failures. Okay? Now I was going to review this material on two-phase commit. I'm going to talk about three-phase commit, and then I'm going to talk about Paxos. They're all very important techniques that are used in fault tolerance literature or systems that want to implement fault tolerance, but they're easy as a protocol but very hard to understand the subtleties of what might happen and so on. So I'm going to give a high-level overview again, go back and try to understand it a little better. At a peripheral level it looks fine, but when you actually dig deeper into what might happen if this fails and then something else fails, you have to actually look at a lot of cases to convince yourself it works under all of those scenarios. Okay? So just to recap, we finished with two-phase commit last time. Two-phase commit is simply an algorithm or a protocol that allows a group of processes to decide whether to commit an operation. It's all or nothing, either everyone commits or no one commits. And you need to be able to do this despite some nodes failing. Okay? And the idea is you have a coordinator, and the coordinator asks everyone what they want to do. It collects all of their responses. If everyone says commit, the coordinator in the round 2 tells everyone to go ahead and commit. If anyone says abort, then the coordinator asks everyone to abort. So it's a two-phase or two-round protocol. There's a phase where you ask for votes and a phase where you announce the results. We looked at the state transition diagram for the coordinator and processes, but I'm not going to go into that again, except to say that there is one major problem with two-phase commit, which is if the coordinator fails, there is no way for the rest of the processes to make progress as to what might have happened. They can't unilaterally make a decision. Okay? This is just taken a pseudocode that is taken directly from the textbook. It just explains exactly what I said, the two-phase process. So you will see that this is the coordinator pseudocode. There are two phases here. You are going to send a vote request saying, tell us what all participants saying, what do you want to do? You want to commit the operation or abort the operation? And then you basically wait and wait for all the votes to come in. And then once all the votes, you record them. When all the votes have come in, if everyone says commit, you say commit, otherwise you send a report. Very straightforward. Exactly what I was just saying. But here is pseudocode for the participants. There are two phases. This is what happens in the voting phase. That's what happens in the second phase when you actually get the the result. Okay. So again, you wait for the vote request, okay, from the coordinator, okay, and then if you can either vote to commit or you can vote to abort. Okay. If you vote to commit, then you also keep logs on your disk just so that you know what you have done. Okay, so that is why it says vote to write to come log, and so if you want to commit, you send a commit request to the coordinator and you wait for the response. And the response is going to depend on what everyone else said. If you vote to abort, you can directly go ahead and abort, because an abort is like a veto. Okay, if you know you voted to abort, you know that everyone else has to abort. They cannot commit at that point. So you don't have to wait for the results of the coordinator, you can abort directly. Okay, that is what was shown here. Okay, if you vote to abort, you can actually, you don't have to wait for the results, you know what the results are going to be. In the other case, you have to actually go to a ready state and wait. Okay, that's what is shown in the pseudocode there. Okay, and that one is the last phase where you wait for the results to come back. Okay, so you're going to wait for the coordinator to announce the result. The coordinator says commit, you commit, it's abort to abort. Straightforward from pseudocode perspective. As I said, last time we went into a little bit of discussion into if the coordinator crashes, it's not possible for the rest of the processes to make progress because they do not know what might have happened. Okay? So you have to wait for everyone to, everyone has to wait for the coordinator to tell you what has happened. Okay? Now, if some other node crashes, not the coordinator, but some other node crashes, then you can still make progress in two-phase commit. Okay, so there are two cases: a node crashes or the coordinator crashes. The coordinator crashes, everyone is stuck. They have to wait for the results of the election to be announced. So then they will just wait until the coordinator recovers. Okay, that may be a long time. But on the other hand, if a process crashes, okay, there is still a way for you to make progress. So if the process crashes in the init states and recovers, okay, then you can then the solution is you can just abort at that point and inform the coordinator, because it is always allowed for any process to vote to abort and go into the final state. Okay. Now, if you recover, if you have crashed in the init state and you recover, you know that you have not actually participated in the election, so election could not have produced the result. Okay, because you have to wait for everyone to vote in order for you to know what has happened. So it is safe for a recovering process in the init state to simply say I'm going to abort and just tell the coordinator my vote is abort, and that will force everyone. Everyone else has to be in the ready state or has aborted the transaction. No one could have actually committed if you haven't even voted. Okay, so it is safe to abort and inform the coordinator. Okay, on the other hand, if you are crashed and you recover and you find yourself to be in the ready state, you can actually do one of several things. Okay, so in particular, you can contact another process queue. You can also contact the coordinator, but let's assume that coordinator is gone away for any reason. You can still make progress at this point because you can contact another process queue, and if queue says commit, yeah, I committed, then P can, the recovering process P can also commit. Because if Q has committed, it means that everyone voted to commit. That's the only way it could have reached the commit state. If Q says, I aborted the transaction, the recovering process P can do the same thing. If Q is also stuck in it, then you can make a transition to abort because of that reason. Meaning that Q can actually abort, and then you can abort as well. And then if Q is also in ready, you keep contacting another participant. If everyone is in ready, that's the case where everyone is waiting on the coordinator who cannot make progress. So that's the problematic state. Everyone is voted and is stuck in the ready state. Okay, no one can make progress. Okay. So that's two-phase commit. Okay. It's a classic protocol from database literature, actually designed in the 1970s, as I was mentioning last time, from Jim Gray. Okay. So there is a generalization of two-phase commit. It's called three-phase commit. Okay, so this protocol adds another phase to the, that is why there are three phases here. So there are 3 rounds of the protocol. Okay? There's a voting round, there is a round that announces the election results, okay? And then there's a final round that says now go ahead and actually act on the results of the election. Okay? So you announce the election results, but you may not actually act on it. Okay, so you are going to actually prepare to act on it, and in round 3 you will be told what to do. Okay, this helps you deal with coordinator crashes, because in this case, there is still a way for other processes to make progress, okay, if the coordinator crashes. In two-phase commit, if everyone is stuck in ready, you don't know what to do. Okay, so you don't want to make a decision. In this case, you can actually make a decision and do something, as we will see. Okay. So this is three phases. Okay, so this is the coordinator state transition diagram, and that's the state transition diagram of a participating process. So in round one, you are going to do the same thing. You are going to ask everyone to vote. Okay, and you are going to coordinator is going to wait. If any process votes to abort, that is the election results are to abort. So you are going to broadcast a global abort and then go into the abort state. Okay. If everyone says commit, okay, you are going to announce to everyone saying that the vote was everyone voted to commit, so prepare to commit. Okay, don't commit yet, but prepare to commit. So you basically make a transition to a intermediate state called prepare commit, where you are actually going to commit after in the next phase, but you haven't committed yet. Okay, this is the addition. In the previous case, you could go directly from the ready to commit. In this case, you are going to go to prepare to commit. Okay, once everyone sends an acknowledgement saying they are all in prepare to commit, okay, at that point, the coordinator is actually going to say, okay, everyone has entered this state, now go ahead and commit, and then you actually commit the transaction. Okay? So you add a step saying, go ahead and prepare, and then say, okay, now do it. Okay? And that's the same thing here. Okay, this is a participant. Initially, you can vote. You're in the Indian state. If you vote to abort, then you can make a direct transition to abort like before. Okay, otherwise, you vote to commit, and then you wait for the results. Okay, if you vote to commit, doesn't mean you will commit. Depends on what everyone else says. If everyone else says commit, you will go to prepare commit state. Okay, send acknowledgements, and then the coordinator will tell you to actually commit, and you will go in. If anyone has voted to abort, then you will be asked to go from ready to abort state. Okay? That's the protocol. Protocol is fairly easy. Okay? You just simply added one more step to the protocol. Instead of 2 rounds, there are 2 phases. There are 3 phases here. Okay? Now the question to ask is, why does this protocol help us deal with coordinator crashes? Okay, why is it that processes can make a decision if the coordinator crashes, and that's still a reasonable decision to make? Okay, in other words, or put another way, what is this extra step bias? Okay, in 2 phases, we added a 3rd phase. And how is this helping us in any way to deal with the coordinator crash? Yes.
You know that if you're in the pre-commit stage, if the process is in the pre-commit stage, then you know that everyone has voted and everyone has voted to commit.
Okay. Okay, so the point is, if you're in the pre-commit state, you know what everyone has voted and what to do. Okay. So the basic way to understand 3-phase commit is, regardless of where you are stuck when a coordinator crashes, you should be able to make a decision that is safe. Okay, so coordinator can crash at any point, and the other processes may be stuck in one of these 3. If you have reached the final state, there is nothing to do. Okay, you already heard from the coordinator. So the problem arises when if you are in any of these intermediate states, you get stuck. And can you make a decision without a coordinator? And is that a safe decision? Okay? So that's the point you want to basically figure out. So the point is, if you get stuck in it, that's fine. You can simply vote to abort. That's safe, because the election hasn't even begun as far as the coordinator is concerned. You haven't even voted. Okay, there is only one transition to final state, so you just decide to abort. Okay. Now, if you are in pre-commit, as was pointed out, the only way you could have gotten to pre-commit was that everyone has voted to commit. That is why you are even in pre-commit to begin with. Okay? In this case, it's also safe to commit if the coordinator crashes, because after you reach pre-commit, you are fine to go ahead and commit. Okay? Now, if you are in ready state, okay, you can then say that since I'm in the ready state, we can go ahead and abort the transaction, because the worst thing that may happen is if the coordinator comes up and says what are the results of the election, that's still okay, because you could have at most gone to pre-commit. You wouldn't have actually committed the transaction. Okay, you would be still stuck in an intermediate state, so you still have time to go and abort. So you will basically, if you're in ready state, it's fine to go ahead and abort. So what this is saying is, or put another way, from any of the intermediate state, there is only one final state you can reach. Okay, from the init, the only arrow that gets you to the final state is abort. From ready, the only arrow that gets you to the final state is abort. And from pre-commit, the only arrow that gets you to the final state is a commit. Okay, so if you make that transition, that's safe because other processes will not have actually gotten to a final state because of you added a pre-commit state. Okay? So that's the intuition. Yeah, basically, you can make progress even if the coordinator crashes, okay, which you could not have done before. Okay, if you're in ready, you don't know which path to take. Okay? You have to talk to others to figure out which path to take. In this case, you can say, I am here, it's safe for me to make this transition, and it's still a fine transition because you cannot do much harm. Is that clear? What the indication is?
I actually don't understand this thing. So once each process decides what they go to ready state.
Sorry, can you repeat it?
Once everyone votes, they go to ready state.
Once everyone votes, you go to ready state.
And then once the coordinator gets accident,
If the coordinator can tell you to abort at that point, or if everyone has voted to commit. If anyone says abort, the coordinator will tell you to abort. Okay? If everyone has voted to commit, then the coordinator will ask you to go to an intermediate state saying, this is what the election said, everyone needs to commit, but you're not going to commit yet, you're going to wait for one more step. to be told.
no, the two phase was that they were putting stuck in the ready state according to the discussion. Why is this passing ready, even if we're putting it?
Okay, so the question is, in the two-phase commit, the coordinator, if it crashed when everyone else is in ready state, there was no way to make a decision. Okay? And the reason is the coordinator can crash, another process can crash. Okay? Anything can happen, and you still need to be able to make a transition. Okay? So the problem there was the case arises where everyone has voted, okay? And suppose that everyone voted to commit, okay? And the coordinator sent the first commit request to the first process, and then both the coordinator and the first process have crashed. Okay? Everyone else has not received the results of the election, they're still stuck in ready state. If at that point you decide to go to abort, that's unsafe because if the first process that crashed with the coordinator came up, then one process is in abort, the others are in commit, and then you have a problem. Okay? In this case, that case is not going to occur because the worst that would happen is coordinator got the results of the election. It told the very first process, let's say everyone said commit, very first process was told to go to pre-commit state, and then the coordinator crashed and that process crashed. In the limiting case, the coordinator and the first process are one and the same because one of the processes is elected the coordinator. So coordinator and that process crashed, so everyone else is stuck in ready. First process is stuck in pre-commit. Okay, but now if everyone else makes a transition to abort, that's still okay because when this process comes up, crash process comes up, it's going to ask everyone saying, what did you do? Okay, at that point, if they told that we aborted the transaction, you can abort the transaction.
So one last question. So when the coordinator is communicating with the processes, is that a broadcast message or is it one-to-one?
Okay. Question is, when the coordinator sends a message, is that a broadcast or one-to-one? That depends on the implementation. Even if it's a broadcast message, the broadcast message could actually be implemented as unicast by the library or some such thing. So it doesn't have to be, this protocol doesn't depend on whether it's sent as n messages or sent as one. Even if you send as one messages, there's no guarantee it will go to everyone. The network can fail or something can happen. So we just have to assume that anything that is sent, any message that can send only reaches a subset of the participants. So you have to make that assumption. Okay. So that is three-phase commit. Again, there are many subtleties, but at least you have the high-level idea as to why this is not as bad. As it doesn't solve all the problems as we'll see, but it's better than two-phase commit. Okay? And I'm going to now slowly get into Paxos, which is going to generalize three-phase commit. Okay? It's going to add, say a little bit about how replication is used in many systems. Okay? So let's assume that you have a server that is replicated. Okay? So there are two ways typically this replication is used. Okay? In one case, you split the incoming request across replicas. Okay? This is the load balancing case. Okay? I have multiple copies of the server running, requests come in, each request is sent to one of the end replicas. Okay? So you take the load, you divide it among all the replicas, so each replica sees 1/n of the request. Okay? This is used for scalability. Okay? Here replication is actually being used for scalability, not for fault tolerance. It so happens that if you have crash failures, if one of those end replicas fails, any remaining request can be resent or the other replicas can take over the load that was being served. That can be done. Okay? But that's all we are trying to do here. So this is suitable for crash fault tolerance. Whatever we have been talking about so far and what we will talk about next, okay, is actually going to apply to technique 2, where each request is sent to all of the replicas. Okay? All of the replicas process the request and produce an answer or a response, and then you are actually checking whether those responses match or not. Okay? The responses match or not, then you basically say this is the answer. The responses don't match, you have to actually do majority or some such thing and then figure out what's the right answer. And this technique, okay, is used for implementing Byzantine fault tolerance. Okay, so you have two scenarios. Okay, I'm going to draw this on the board here. Okay, let's say the 3 servers, requests come in. Okay, in scenario 1, the request is split. So you have 1/3 of the request going here, 1/3 going here, 1/3 going here, and then each replica only sees some portion, fraction of the requests that are sent to it. Okay? That's this technique. This is used for scalability, load balancing, and if one of the server goes down, these requests that are going here can be re-split and sent here. So the other 2 servers takes over the load. Okay? So that's crash fault tolerance. Okay, what we are talking about is a separate scenario here. When there is 2-phase commit or 3-phase commit of Paxos, you basically send each request to all of the replicas. Okay, all the replicas, so compute, process each request. Okay, they all produce answers. Okay, and then you are using 2-phase, 3-phase or Paxos to vote and say what is the right answer to send to the client. Okay, that's the scenario we are using replication for. Okay, most systems actually do this. If you want to use BFT, you have to actually do this. So in this case, adding replicas hasn't allowed you to scale up, as you will see, because each request is processed by all the replicas. It's being used for implementing Byzantine fault tolerance or handling malicious problems or faults that can occur in the replicas. Okay, that's the thing to keep in mind. Okay, is that clear? So with that in mind, let's talk about Paxos. So first we'll talk a little bit about what might go wrong even with 3-phase commit and then see why you want Paxos. So Paxos is a class of protocols. It's not one, but it's a class of protocol that is basically belongs to this domain of what's called consensus or agreement. Okay? You want a set of servers to agree on an answer. Okay? This could be database servers, there could be web servers, it doesn't matter what the servers are. A request goes in, you send it to all the servers perform the same computation, they produce an answer, and you want to figure out what is the right answer. And so if some small fraction of them are faulty in any way, then you still want to be able to send the right answer. Okay, in this case, if there's a fault here, meaning there's a bug, produces the right answer, you are going to send the wrong answer, you're going to send the wrong answer off to the client, because only one server is processing the request. Here, every server is processing every request, so we get the chance to vote on things. Okay? So if you remember very early on in the fault tolerance discussion, I showed you a circuit, which as we said is triple modular redundancy. Every request was sent, every phase was replicated thrice, every request was sent to all 3 voters that voted on it and so on. And that's the same idea we're going to actually implement here, in some sense. Okay, so that's why we have this application. Okay. So the thing to keep in mind is, so you want to arrive at a consensus on what the answer is, or it's also called agreement. You want to agree on an answer. Okay, this is what Paxos is going to allow us to do. Okay, essentially you want to achieve reliability in the presence of faulty processes. You need processes to agree on the data value for a computation. Okay. And what you agree on doesn't matter. Paxos can also be used to implement a better version of 3-phase commit. If you want to just agree on whether to commit, not on the value of a request, but whether to commit, you can use Paxos. So the agreement is whether to commit. If the agreement is what is the response to this query, that's another kind of agreement. So you just want to agree on something. And here are the properties we want. Okay? So agreement says every correct process agrees on the same value. If a server is actually functioning properly, they are all going to produce the same value. Okay, that's one. You want termination, okay, which means you want to actually produce a result at the end. Okay, you want, so if you send a request, you want an answer, so that means you're going to terminate. You want validity, which says that if all of the servers say the right answer to this question is value V, you want all processes to agree on V. Okay? Just agreement doesn't mean anything, because the trivial protocol is let us agree that for no matter what the request is, the answer is 1. Okay, that's agreement, because you're agreeing on it. Okay, that's not going to get you what you want, because you want to actually agree on the right answer, not agree on any answer. Okay, so this is validity says if you actually compute value V, okay, then you should actually agree on V, not agree on some arbitrary value that makes no sense for the question that you are asking. Okay. And integrity says if every correct process decided on at most one value and it decides V, someone must have proposed V. Okay, meaning that if you have a right value V, somebody should actually propose it. Okay. So these are all basic properties of the protocol that we want. Okay. They are all related, okay, but they are all important properties. Okay. We won't go into how all of those come about, but these are some standard properties you want from any consensus protocol. Okay. Agreement, termination, validity, and integrity. Okay. So now with that, let's ask, why can't you use two-phase commit or three-phase commit to agree? Okay. So far we looked at two-phase commit and three-phase commit for a particular purpose, which was whether to commit a transaction. But think of using the same voting phase to agree on any computation. Okay? You send a request, you produce a value, the coordinator says what was your answer, they all send the answer, and the coordinator says this is the answer. You can generalize, rather than saying commit or abort, you can just ask what was the answer to this query or what was the answer to this request. So you can easily generalize 2PC or 3PC to agreement protocols, but the question is what might go wrong. Okay, you know that the main problem here is your safety is ensured but liveness is not. Okay, which essentially says you won't do anything bad, but if there are crashes, nothing good may happen. You may just get stuck. Okay, that's the main problem. Okay. And we saw that in two-phase commit, okay, you basically the coordinator needs to be up. If the coordinator crashes, you may get stuck in ready state. You cannot make progress. Okay, that's going to impact liveness. Okay. Because you're stuck, you're not doing anything bad either. You're not producing values that disagree or cause some problems, but you are not doing anything good in the system. Okay, the coordinator needs to be up for liveness. Okay. Three-phase commit handles coordinator failures. Okay, that we saw, but it doesn't handle network partitions. Okay, what that essentially says is if you have a set of processes and a coordinator, and in the midst of this three-phase protocol, if you actually have a network partition where some processes are now in one side of the partition and other processes are on the other side, you may actually have problems in this case. Okay. The main problem is what might happen is the coordinator may have sent a pre-commit to some processes, other processes are stuck in ready. Okay. Now if you're stuck in ready and you go into an abort, and the pre-commit ones, if they're in a majority and they decide to commit, then you have a problem where you basically, on the two sides of the partition, you reach two different decisions. Okay. This is the reason why in three-phase commit and two-phase commit, you want everyone to agree, not just the majority to agree. Okay, so you cannot make some simple generalization to three-phase commit saying there's a partition, if the majority are in pre-commit, let's commit. You want actually everyone to figure out what's going on. Okay. Now Paxos tries to generalize some of these ideas and address this limitation. In Paxos, it's the majority rules. Okay, it's not absolute. It is not everybody doesn't have to agree, but a majority have to agree. Okay. So you're going to take the majority vote. Okay, no one has a veto or anything like that. So you want, so because of this, we are going to be able to actually reach a final state, even if some processes are crashed. If you want everyone to participate, if that one process crashes, everyone else is stuck. Okay. So you want to go with majority and say if you go with majority, bad things are not going to happen. Okay. So I'll talk about the protocol. The protocol is actually straightforward, but there are many subtleties that are actually hard to explain and even harder to understand without sitting back and thinking about it and working through examples. Okay, but I'm going to try a few different scenarios and subtleties so you get to understand a little more about what Paxos is trying to do. Okay. So what the goal here is going to be to let some nodes agree on the value of a computation or a value of an operation, even in the presence of some nodes failing, okay, some networks failing or networks causing partitions, or there being arbitrary delays in the system. Okay, so you want to be able to reach a final thing. Okay. So there are many use cases. This is often even used for leader election, for example. Okay. You can use Paxos to agree on. So you are trying to reach agreement. Agreement could be let's agree on the leader, let's agree on whether to commit or abort a transaction, or let's all agree on what the result of a query was. Okay. So what you are agreeing on is almost not is orthogonal from Paxos. Paxos is just a voting and an election protocol. What you are trying to elect or vote on is independent of Paxos. Okay, that's the thing to keep in mind. Okay. It's a fairly general approach, and there are many variants of it. Okay. It was proposed by Leslie Lamport and Barbara Liskov. It is actually used widely in many real systems. They don't actually use two-phase or three-phase commit because of their blocking properties. But Paxos is what they actually end up using, because if majority can vote, then you can still make progress even if some nodes are failed. Okay, that's the basic idea. Then we'll see it looks very similar to three-phase commit in terms of its elections and rounds and so on. Okay? And here are some properties that you will see Paxos provides. I won't prove these, but these are what you want. Okay? So the safety or correctness properties are all nodes that are actually working are going to agree on the same value. Okay? So that's agreement. Okay? And if you agree on some value, then some node propose that value. Okay? So if you agree that the query result of this computation should produce value 10, then some node should have actually proposed that I perform the computation and my result was 10. Otherwise, as I said, a trivial solution to Paxos is, regardless of what you ask, my answer is always going to be 1. Okay, so that's going to allow you to agree. Doesn't matter, you don't even have to do the computation. Okay, so you always agree. So you want to basically say you agree, but then if you agree on something, at least some node should have produced that as a result of this computation. Liveness property, which is where we make progress, says if less than half the nodes fail, which means if the majority of the nodes are up, they are eventually going to reach agreement. Okay, eventually they will converge. Okay, it may take some arbitrary amounts of time, but they will converge. Okay? And now, in this case, liveness is not guaranteed if there are steady stream of failures. Paxos is not going to converge if during the protocol node keeps on failing. Okay, so each node failure is going to cause you to restart Paxos, and if you keep on having failures, you are not going to converge. Eventually, you will have less than half the nodes even up, so you can't even reach majority vote. Okay, so this works only if you have some nodes failed. Okay, minority of the nodes are failed, but then you are in steady state. No more nodes are failed. So that's basically what you have to keep in mind. Okay? And the reason we have to sort of worry about all of this is we can assume that anything can go wrong, which are the following. Network may get partitioned, some minority of the nodes may disappear, they may not be reachable, leader may crash, okay? So new leaders can be elected, and then your new leader may come up and say, I decide that this is the new value, even though the old leader was proposing a different value. Okay? So you can also have more than one leader being elected, and you still want to reach agreement. Okay, so if one leader has failed and come back up, there's another leader, they're all proposing, Paxos should still allow you to convert. So all of these things can go wrong. So you still want the ability to reach agreement. Is that clear? What we're trying to do. How we do it, I haven't said anything yet. Okay, so with that, I'm going to delve into a little bit about how the technique works. So there are going to be 3 entities in the system. There's a proposer, which is the leader, there's an acceptor, and there's a learner. We are going to ignore the learner for now. Okay, essentially, we'll only talk about two nodes. The one that is going to ask is the leader, and the others are the ones that are actually going to vote. Okay, so those are the acceptors in this case. Okay. And we will assume the following. We'll assume that each round of their election, we'll call it a proposal. Okay, and they will have proposal IDs, which are going to be monotonically increasing. Okay, you cannot have two proposal IDs to be the same. Okay, so proposals are ordered by proposal number, and then nodes can pick any monotonically increasing one, but you cannot pick a value that somebody else has picked. So we'll assume that any time you say, I performed this computation, this is my result, you have to attach a proposal ID to it. So this is, think of it as answer number or answer ID. Okay? Answer IDs have to be unique and they have to be monotonically increasing. Okay? And we can assume we know how to do that. You can always pick a unique ID for, it's like a sequence number. Okay? Essentially you have to assign sequence number to your answers and they have to keep increasing. Okay? And we basically assume that if you once you accept a proposal with value V, all higher proposals are going to have that value. Once you accept something, you are going to keep it, and you'll see how that is done. Okay? There are several variables here that I'm going to come to. Here, NA is the sequence number, V is the value. That's N stands for sequence number, V is the value you are accepting. Okay? This is the highest sequence number we have seen in the system, so I don't know, right? And then my N is my proposal number, which I'll talk about. So there's three phases, like three-phase commit. Okay? First phase is you ask for a value. Yeah, there's some code here, but it's pseudo code, but it's essentially straightforward. Okay? So the leader essentially sends a prepare message, okay, with the sequence number, saying, let us vote. Okay, and here is the sequence number. Now, upon receiving a prepare message, which is saying vote, okay, and a sequence number, if you basically have seen a higher sequence number already, okay, you just essentially say reject. Basically, anything may have happened. Another leader may have gotten elected and started a new election. So essentially this says, when I receive a request to vote, if I have seen a higher ID request to vote on, then this is an old request. There's no point in even answering this request. So let's say reject because some new election has already started after this election. Okay, so any old messages are discarded. I've already seen a higher ID proposal. Okay. So now that's just a sanity check saying you want to do monotonically increasing election. Otherwise, what you're going to do is you set your proposal number to the one that was sent here. That's the election ID, saying that is your proposal ID, and you send back a reply. Okay, the reply says prepare OK, saying I'm fine. Here is the value, okay, of the proposal, and here is the value of whatever answer I want everyone to accept. Okay, so this is what I computed. And this is essentially end of it. Okay. Or if you already accepted in a previous round some value, you can again, instead of computing it, if you accepted somebody else's value, you send it. Okay, saying this is what I value accepted so far, and this is the proposal ID. Okay, so that's the prepare phase. You're just voting at this point. Okay. Now the leader is going to get responses. Okay. If it gets a reject response, then it says I cannot get anybody to agree there. Rejected this election, you can start a new election if you want to know something. Okay, or if you get an OK message from everyone, from at least the majority, not everyone. If you get an OK message from the majority, what you are going to do is you are going to take the non-empty value from the highest ID. Okay, you can pick a value. Okay. Here you can figure out, you can actually compare them if you want. Okay, and pick the majority. Okay, or you can pick the highest ID and try to get everyone to accept it. Okay. If you are allowed to set null as your request, and I don't know what value you pick. If you are null, then as far as the protocol is concerned, the leader can pick whatever value it wants. Okay, and now what you are going to do is you are going to try to get everyone to accept this value. Okay, so you are going to send an accept message, okay, which basically says that take this new value and set it to the value of the computation. Okay, so you vote, you get those values. If the majority have voted, you pick a value from that vote and you get everyone to accept that. The reason it is written in this generic way is because the operation could be anything. It could be I pick a new leader, Paxos, I decide what the output of the query is, and so on. Okay, so how you pick this value Okay, in this case depends on what computation you're trying to actually, what operation you're trying to reach agreement on. Okay? If it's database queries, you should actually match the queries and pick a value. Okay? If it's leader election, you can pick a unique value and say, here is who will choose leader as the leader for something else. Okay? If it's abort or commit, as part of two-phase commit, you're going to actually pick based on what you voted. Okay? So that is not mentioned as part of the protocol. Okay? You can pick a value and you can assign that value. And that is done separately. And our technique is merging with that. Okay, so this is the third phase, where after you receive the accept message, what you are going to do is you can check in the midst, did anyone else, was there a later election that started? If so, you are going to reject it. Yes, I cannot accept your value because a new election has started already, and so this value is no longer valid. But if this is still the latest election, then you are going to say, this I will set the value to whatever you proposed. Okay? I'm going to set my sequence number to your sequence number and send back an OK message, which is saying I'm okay accepting this value. So that's phase 2. And phase 3 is basically the commit. So that was equivalent to the pre-commit. Yes, I am okay accepting the value in phase 3. If you get an okay, accept okay of an act for all that, then you say decide, saying let's finalize this value. Okay, so that's the third phase, which is equivalent to the 3-phase commit. Okay, so you vote, you get a value, okay, and then based on that value, if everyone is okay with the value, okay, you are going to be asked to decide on that and say this is the final value. Okay. So 3 rounds, just as you have a 3-phase commit. Okay, so now there are many subtleties here that are sort of not something we are going to go into in terms of groups and so on, but here are some properties. Okay? We want each proposal number to be unique. I already mentioned that. Okay? The other thing is, because we are looking at majority, okay, what is guaranteed is if the majority have agreed that this is the output of the operation, if the remaining minority come by and try to agree on something else, they will not be able to do so, because there will be at least one acceptor from the majority that will have to be part of their group to have enough nodes to agree on something, and there will be disagreement about it. Okay? So it says any 2 sets of acceptors have at least one node in common. This is similar to what we did when we did Gifford's quorum-based protocol. If you remember, in quorum-based protocol, we needed a quorum to agree on the value of an operation. Okay, does anyone remember Gifford's protocol? Yes. So let's write that down. If you remember, I had an example I took from the book where there were 12 or so nodes. Okay, we were trying to do reads or writes. Yeah, we said that we could pick a read quorum and a write quorum. A write quorum had to be strictly greater than half, and read quorum was such that NR plus NW was greater than. And we basically said that if some majority of the nodes have seen the write, okay, to a file, and then if you ask the other nodes, you need a majority of the quorum to agree, so at least one of the nodes will disagree, because from your minority you have to pick one from the other set, and that will disagree with you. So you can never have a case where your 2 majorities both agree, because if you have, by definition, majority is more than 50%. If the others try to get you to say that the result was something else, to actually have majority, you have to pick one from the majority set, and that node will disagree with you. Okay, so that is what it is. 2 sets of acceptors will always have a node in common, so you cannot agree on 2 values. You only agree on one. Okay. And this was the value set in phase 2 is the value of the highest number proposal received in phase 1. Okay, so that is simply saying that the values are so this basically says, because the sequence numbers are monotonically increasing, if once you agree on a value and you get a decide, then you will basically propose the same value each time. Okay, you cannot change that value. Okay, that is essentially what that is saying. Okay, so let me see. There is a quick example which is showing the 3 phases. Okay, so here we have 3 nodes. nodes N0, N1 and N2. N1 has been chosen as the leader and your two nodes N0 and N1. Okay, so initially you get a prepare message, okay, which says vote, okay, and then you may actually initially choose to vote null, saying I want to perform a computation, or you can propose a value. It doesn't matter what you do. In this case, you are going to actually just vote null. Okay? And if you vote null, then the leader can pick whatever value it wants, okay, and say this is what we agree on. If you actually propose a non-null value, then you can look at the majority and decide. How you decide what the value is up to the leader. Okay? In this case, it's just showing that you voted null, and then the leader picks a value for it. Okay? And the leader then tries to get everyone to agree on this value. So you pick value 1 and it says, let's accept value 1. Okay? The other nodes can then say yes or no. Okay? The other nodes can say, I don't like this value because it disagrees with whatever I computed, or you can say, I like this value, I agree to your value. Okay? So in this case, so if you are actually performing computation, at this point you can say, I perform the computation, you propose some value, it doesn't match with mine, so I could say no. Or you can say, you propose this value, it matches what I did, so I can say yes at that point. Okay? So if everyone says yes, as I shown here, you say then okay. In the last phase, you say everyone has said okay to the value that was proposed, let's all agree on. Okay? And you reach agreement at that point. Okay, is that clear? So that's the basic protocol. I'm going to put up a couple of papers that have actually explained this. The original paper on Paxos is very hard to understand. Okay, the original paper actually doesn't even use the term Paxos, it refers to this problem as a part-time parliament. Okay, so it's essentially the same thing. And what the part-time parliament problem basically is let's say that you have a legislative body that wants to make some laws. Okay? And let's say all the legislators are part-timers. So they show up at random points in time. Okay? At some point there is some legislators show up but others don't show up, but you all want to reach agreement. Okay? So the question is, how do you actually have a protocol that allows you to reach agreement? It's the same as Paxos, where not showing up is the same as failing. Okay? So that's the original paper. Hard to understand, and there was another subsequent papers or many papers written that tried to explain this idea in a simpler way, and there's one called Paxos Made Simple that I will put up. It's not that simple as you'll see, but it's simpler than the original paper. So read that, and then I am going to put up another paper which criticizes Paxos as being still too hard to implement and get right. So there is a alternative approach which is a variant of Paxos. There are many different variants of Paxos. So there is a generic protocol. It leaves many things unsaid as to why should we actually send null or you send something else, how we pick the value here. There are many things that are unsaid. So in a real implementation, you have to make those decisions. So depending on how you implement Paxos, you get many different variants. Yeah, so there's one paper I'm going to put up which tries to criticize this as leaving too many questions unanswered, and it proposes a slightly different approach. Just as a way for you to understand how systems are going about implementing this ideas. Okay? Any questions? So there are many issues that I'm not going to go into, which says here is network partitions, timeouts, etc. which you will do to try to figure out if you can from the paper. But what I will instead talk about is switch gears a little bit and talk about this problem of recovery, checkpointing and logging. Okay. So we are done with the discussion of two-phase commit, three-phase commit and Paxos. Yeah, of the three, you will see that Paxos is by far the most popular one. If you have real distributed systems such as the ones that companies like Google and Facebook and all of them build, they are based on replication, and you send requests to multiple replicas and you get responses. They all have voting in somewhere in them, and Paxos is basically how they go about doing it. Yeah, so it's something you should at least know at a high level. Yeah. When you implement it, there are a lot more decisions to make than what the generic protocol asks you. Okay. So, but that's what those class of techniques do. we are going to switch gear a little bit and talk about the problem of recovery. Okay? What we are talking about was agreement and consensus. Okay? So this is a different problem now. Okay, we are done with agreement and consensus. We are now looking at the problem of how do you recover after a failure. Okay, what techniques can you use to recover from a failure? The simplest approach that is used to recover from a failure is something we have already encountered when we talked about distributed snapshots. If you remember when I was mentioning distributed snapshots, I said processes should periodically snapshot their state. You should do this for a consistent snapshot or a consistent cut. And if any process crashes, you terminate them all. You restart them from the most recent snapshot. So this is a technique that is general enough that it is used in many scenarios. So essential idea is when you have a process or any application that's either replicated or not, you should periodically checkpoint your state to disk. Whatever you have in memory that can go away, you put on disk, which is stable storage. Okay? So essentially stable storage is something you can get back to even after the process has failed. Okay? Upon a crash, you can roll back to the most recent checkpoint that has a consistent state. That's the first idea behind checkpointing and recovery. And there's a picture here somewhere, which is here. So here is basically what is being shown. There are two processes. Processes are sending messages to one another, and periodically, so there's black lines are checkpoints. Okay? So you periodically checkpoint your state. Okay? And if there is a failure, which is process P2 has failed, then process P2 and P1 are restarted from their most recent checkpoint, okay, which is P2 is going to start here, P1 is going to start here. And if you remember when I was describing this in the context of distributed snapshot, I said you have to be careful in how you take these checkpoints. Okay? Because first is we assume there is no global clock. Okay? There is no perfect synchronization which says all processes should take checkpoint at precisely the same time. That would be ideal, because then you are synchronized, you start from exactly the same point. Okay. But there is no global clock as we have seen. So what distributed snapshot allows you to do is, even in the absence of clock synchronization, you can take these checkpoints, but then they are consistent in some sense. By consistent, it means that you have taken checkpoints of all the processes memory state, and you have taken you have copied all the process messages that are in transit. Okay. So no message is going to be replayed twice, or you don't miss any messages. Okay. That was the problem of consistent checkpoint. Okay. So you can do this. Okay. So this slide is titled independent checkpointing, but as I just argued, if you do this completely independently, you will get bad results. You can't arbitrarily start any process from wherever it wants. Okay, that's not going to give you the desired result. So you want to ensure that inconsistencies are gone. Okay? And that you use distributed snapshots to implement, which is what we discussed in lecture 11. Okay? So the idea is the basic approach, okay, and we'll try to improve on that approach, is you periodically take checkpoint and then you roll back to the most recent checkpoint. Now there are many problems with this approach. It gives you what you want, but there are issues. First problem is taking checkpoints are not easy when they are expensive operations. Okay? Think about your process with 2 gigabytes of RAM. Okay, that it's using. Okay? Taking a checkpoint means literally taking that entire 2 GB and writing it out to disk. Okay? So let's say you decide to checkpoint every 5 minutes. So now every 5 minutes you have to pause that process, okay, and write out 2 gigabytes of data to disk. That's a high overhead to pay. Okay. It also consumes a lot of disk space and so on. Okay. So checkpointing tends to be an expensive operation. Okay. So if you checkpoint, then you would not going to do it every 5 minutes. You may do it once every few hours or once a day. Okay. Because then you can say, I amortize it over a much longer period. I don't do it very frequently. The downside to that is the less frequently you checkpoint, the more work you lose. Because if something crashes, you are going to restart from the most recent checkpoint. Okay? So essentially everything that has happened since the checkpoint has gone, you have to redo that. Okay? So you have a trade-off. The more frequently you checkpoint, okay, the more the overhead of checkpointing, but less work you are going to lose, less you have to redo. But since checkpoints are expensive, if you do it less frequently, then you are going to lose more work, but the cost of checkpointing is. So there is a lot of work in the fault tolerance community that says, how do you bridge this gap? Okay, how do you actually deal with this issue of, I don't want to lose work as much as possible. Okay? So there is a lot of work that basically uses other techniques to do this. The other technique we have seen so far, in addition to checkpoint, is logging, which is to keep a log. Okay, you can always replay the log from the log or to redo the new operations. If you remember when I was talking about transactions and so on, I said you can keep a log and then you can roll back the log and undo the effects. Databases use logging all the time. Okay? Modern file systems also use logs. Okay? So what happens in a log-based approach, okay, which is an alternative to a checkpointing based approach. In a log-based approach, what happens is before you do any operations, okay, you say this is what I am going to do, and you write it in a log. Okay. The log is actually kept separate from the main system. Okay. That way, if the main system goes down, you still have the log. Okay. Now, if your system fails, you can essentially recover the state of the system by repeating all the operations in the log. This is called log replay. Okay. This is how a database would recover, for example. If the database crashes, every query or every record that has been updated, there's a record of it saying, I went to this record, I wrote this value. I went to this record, I wrote this value, and so on. Okay? So now if the machine crashes, you can actually figure out everything that has happened. Okay, you can go to some old backup, you can take the backup, and then you can start replaying from that value, and you can catch up. Okay? So in this case, once you do the log replay, no work is lost because you recovered the system to the most recent log update. Okay, so this is a standard database approach, okay, which is also used in fault tolerant systems. So as I said, databases and sources. So if a node is going to fail, any requests that are in progress that haven't completed, they are going to be lost because they haven't committed. Maybe transaction or request that are committed. But anything that else, you can just go into the log, which will show you the history of everything that you have done to modify the system, and then you can basically repeat those operations from some previous consistent state, which could be just a very initial state or any intermediate state. Okay, so these are the two approaches that you have. Okay, you have on the one hand checkpointing, which doesn't keep anything that has happened. It's a periodic snapshot. Okay, it says at time t, this is the state of the system. Time t plus 1 hour, this is the state of the system, and you can recover them. Okay? Logging is an alternate approach where you keep track of everything that's happening over time. Okay? In case of logging, recovery takes more time because you have to do a log replay. Okay? The log is long. Let's say it's a busy database. You may have 10,000 queries in the log. You have to actually go through the log and repeat whatever this 10,000 queries did, and then you have recovered the state. Okay. So checkpointing during normal operation is expensive, okay, but recovery is cheap because you just load the most recent checkpoint, you're ready to go. Okay. Logging, runtime operation is cheaper because you're writing little bits to a log saying I did this, I did this, I did this, but recovery is more expensive. Okay, because you have to then go through a potentially long log and then re-roll it forward. Okay. So now as you can imagine, you can actually combine the two approaches, which is basically saying that I can combine checkpointing and message logging to get the best of both worlds. Okay? So I can now, in this case, what is going to happen is I'm going to periodically checkpoint. Okay? And I can choose the period based on how much ever cost I'm willing to pay. You don't have to checkpoint every 5 minutes, but let's say every 6 hours, every once a day, you can do the checkpoint, whatever frequency you pay. Okay? So since every time you take a checkpoint, you start a new log. So from the checkpoint time, every operation that has changed the system, you are going to keep in a log. Okay, is that clear? So now if you want to, if some system crashes, the way you are going to recover, so you are going to go to the previous checkpoint and you say I'm going to load that state. But then I don't have to start from that because I know what has happened subsequently, it's recorded in my log. Okay? So I'm going to use the log to roll forward from that point. Okay? And I can get to the most recent point. Okay, so I'll show a quick picture. show how this might work. Okay, so that's basically a more modern approach that. So here we have done. Okay, so these are your checkpoint intervals. So you do a checkpoint. Okay. So in what happens in a checkpoint, if this is the process's memory, you're going to simply write it out to disk. Okay, so entire snapshot of the memory contents as well as messages in transit are actually put on disk. Okay. So essentially, if you have any crash at any point, you're going to lose this much work because you can only recover to that point. Okay. So now what you have done is, in addition to checkpointing, you're logging, which says I take this checkpoint and any small writes that occur afterwards I'm keeping in a log file. Okay. So basically now if the system crashes at this time here that are marked by NX, you're going to the disk, you're going to take the checkpoint and recover. Okay. So that will recover the system to this point in time. Okay. And then you take the log and you look at all the operations and you apply them to memory, which will roll it forward. So you will basically do exactly what the real system did. You are emulating it by replaying the log. Okay. And then you will go to the most recent log value and you are going to recover from that point. Okay. So that's a better approach in that you can basically combine checkpointing, which is going to basically allow you to replay or recover the system to a given point in time, and you're combining logging. Okay. If you had only logs, what would have happened if you had crashed at this point? You would have started with the empty state from time 0 and replayed the entire log. Okay. That may take a long time, so recovering will be slow. So by using the most recent checkpoint, you've accelerated that process by saying, I've already recovered the system to state time t rather than starting from time 0. And then I have a smaller log to replay. So the recovery is faster. Okay, so you combine these and you get lower trade-offs over. Okay, so there are many modern systems that will essentially use combination of checkpointing and logging to achieve their goals. Okay, any questions on this? So I think I have actually run out of material for fault tolerance. I think the next topic is distributed file systems, but I don't actually have the slides with me. So I'm going to end today's class early. And we're going to start distributed file systems starting Wednesday. So there are, just to keep you sort of abreast with where we are, we have to do distributed file systems. Then we are going to have a couple of lectures on World Wide Web. And then the last 2 lectures are going to be on distributed middleware, okay, where we are going to talk about various kinds of middleware, including Blackboard architects. Okay, and there's going to be one special class or special lectures on data, guest lecture, special and then a guest lecture on cloud computing and data centers. Okay, so that one is going to be 2 weeks from Wednesday after Wednesday, from 2 weeks from this Wednesday. Okay. So that's basically what is remaining. Okay, we are about 6 lectures away from getting done with all of the material. And I have one more announcement, or not an announcement, a question to you. If you are interested, I can add an optional activity to the class, which is to go and visit a real data center. Okay. There is one that the university has built in Holyoke, which is about 10 miles from here. They occasionally arrange for tours where you can go and actually see the machines in the data center and so on. Okay. It has nothing to do with the course itself, but because we have talked about data centers and clouds and whatnot, if you have an interest, I can arrange for a tour for this class. We'll have to carpool and go there, okay, some afternoon, and go see the data center and come back. So let me know if you have interest, send me a mail, I can arrange for that activity. Okay? So that's something we can, the date, etc., we can decide. At this moment, I'm simply asking if there's enough interest for some group of you to go to this facility and look at it. Okay, just to understand how data centers, what they look like. Alright? Okay, so let's stop here today. Continue next time.